I have spent much of my life thinking about the atom, about what happens in those infinitesimally small spaces where matter reveals its deepest secrets. And if there is one phenomenon that captures both the strangeness and the profundity of the quantum world, it is what we have come to call the quantum jump. This idea, this discontinuous leap of an electron from one state to another, has been at the heart of my work, my debates, and my understanding of nature itself. Today, I want to share with you not just the physics of these jumps, but the journey of thought that led us to understand them, and perhaps more importantly, what they reveal about the very nature of reality. Let me begin with a confession. When I first encountered the problem of atomic structure as a young physicist in the early years of the 20th century, I was troubled. Deeply troubled. The classical physics that had served humanity so well, the physics of Newton and Maxwell, seemed utterly incapable of explaining the atom. According to the established electromagnetic theory, an electron orbiting a nucleus should continuously radiate energy, spiraling inward in a fraction of a second until it collapsed into the nucleus itself. Yet atoms were stable. They existed. You and I exist because atoms are stable. This was not a small problem to be swept aside. It was a fundamental crisis. I arrived in Manchester in 1912 to work with Ernest Rutherford, who had just a year earlier proposed his nuclear model of the atom. Rutherford had shown through his famous gold foil experiments that the atom consisted of a tiny, dense nucleus surrounded by electrons. It was a beautiful picture, like a miniature solar system. But it was a picture that made no sense according to the physics we knew. The contradiction was stark and unavoidable. Now I must tell you about the clue that changed everything. It came from spectroscopy, the study of light emitted by atoms. When you heat a gas of hydrogen atoms, for instance, they glow, and if you pass that light through a prism, you see not a continuous rainbow but distinct, separate lines of color. These spectral lines had been catalogued for decades. There were even mathematical formulas that described their patterns. In 1885, a Swiss schoolteacher named Johann Balmer had found a simple equation that predicted the wavelengths of hydrogen's visible spectral lines with remarkable accuracy. But no one understood why this formula worked. It was empirical, descriptive, but not explanatory. Then came the quantum hypothesis. Max Planck, in 1900, had introduced the radical idea that energy in electromagnetic radiation came in discrete packets, which he called quanta. The energy of each quantum was proportional to the frequency of the light, with the proportionality constant being what we now call Planck's constant. A few years later, Einstein extended this idea to explain the photoelectric effect, suggesting that light itself consisted of these quanta, these particles we now call photons. But these were ideas about light, about radiation. The connection to the atom was not yet clear. In 1913, I published a paper that brought these threads together. I proposed that electrons in an atom could only occupy certain discrete orbits, each corresponding to a specific energy level. This was the crucial step, the break with classical thinking. An electron could not spiral gradually inward because it could not lose energy continuously. Energy could only be emitted or absorbed in specific amounts, in quanta. An electron could jump from one allowed orbit to another, and when it did, it would emit or absorb a photon whose energy exactly matched the difference between those two energy levels. This was the quantum jump, though I must say the term itself came later and I was never entirely comfortable with it. The word jump suggests something sudden and discontinuous, which is true, but it also invites questions about what happens during the jump, about the trajectory of the electron as it moves from one state to another. And here is where we must be very careful, because the quantum jump is not like a ball flying through the air from one hand to another. There is no path, no trajectory in the classical sense. The electron simply ceases to exist in one state and begins to exist in another. The transition itself is, in a profound way, not part of the continuous unfolding of events that we are accustomed to in our everyday experience. Let me explain why this model works so beautifully for hydrogen. The energy levels I proposed were quantized, meaning they could only take on certain discrete values. I derived these values using a combination of classical mechanics and the quantum condition that the angular momentum of the electron could only be an integer multiple of Planck's constant divided by 2 pi. This may sound arbitrary, and in some sense it was. I was proposing a rule, a postulate, because it worked, because it explained the data. The allowed orbits corresponded to specific radii and specific energies, and when an electron jumped from a higher energy level to a lower one, it emitted a photon whose frequency was given by dividing the energy difference by Planck's constant. The beauty of this was that it explained Balmer's formula and all the other spectral series of hydrogen. It predicted them from first principles. The spectral lines were nothing more than the photons emitted when electrons made transitions between different energy levels. Each line corresponded to a specific jump. The red line in the Balmer series came from an electron dropping from the third energy level to the second. The blue-green line came from the fourth to the second. And so on. The agreement with experiment was extraordinary, precise to many decimal places. But let me be honest with you about the limitations of this model. It worked perfectly for hydrogen, an atom with just one electron. But when we tried to apply the same ideas to helium, with 2 electrons, or to more complex atoms, the mathematics became intractable. The model was not complete. It was a mixture of classical and quantum ideas, what we sometimes called semi-classical or old quantum theory. It was a stepping stone, an essential one, but not the final destination. The deeper question that troubled me, and that I debated at length with Einstein and others, was about the nature of the jump itself. When does it happen? How long does it take? What determines when an electron will jump from one level to another? According to my model, an electron in an excited state would eventually jump down to a lower energy state, emitting a photon in the process. But when exactly would this happen? The theory gave probabilities but not certainties. We could calculate the average time an electron would spend in an excited state before jumping, but we could not predict the exact moment of any individual jump. This probabilistic character of quantum mechanics was something Einstein never accepted. He famously said that God does not play dice with the universe. I understood his discomfort, but I came to believe that this indeterminacy was not a flaw in our theory but a fundamental feature of nature itself. The quantum jump is inherently unpredictable. We can know the probability, but not the certainty. This was one of the central insights of the quantum mechanics that developed in the 1920s through the work of Heisenberg, Schrödinger, Dirac, and many others. Heisenberg's uncertainty principle, which he formulated in 1927, made this even more explicit. You cannot simultaneously know both the position and the momentum of a particle with arbitrary precision. The more precisely you know one, the less precisely you can know the other. This is not a limitation of our measuring instruments. It is a fundamental property of nature. And it has profound implications for understanding quantum jumps. When an electron is in a particular energy level, it does not have a well-defined position in the way we think of classical objects having positions. It exists in what we call a quantum state, which can be described mathematically by a wave function. This wave function gives us probabilities for where we might find the electron if we were to measure its position, but before the measurement, the electron is in some sense spread out, existing in a superposition of possibilities. Now, when a quantum jump occurs, the electron transitions from one quantum state to another. But we must resist the temptation to visualize this as a little particle hopping from one orbit to another like a flea jumping between 2 rings. The quantum state is not a trajectory. It is a description of what we can know about the system, of the possible outcomes of measurements we might make. Before the jump, the electron is in one eigenstate of the energy. After the jump, it is in another. The transition itself is instantaneous in the sense that it is not a continuous process that unfolds over time in the way that classical motions do. But here I must add an important nuance, something that has been clarified only in more recent decades, though the seeds were there in our earlier work. The quantum jump is not truly instantaneous in every sense. When we measure atomic systems with sufficient precision and speed, we find that the jump does take some time, though it is extraordinarily brief, typically on the order of nanoseconds or even faster. During this time, the atom is in a superposition of the initial and final states. It is neither fully in one nor fully in the other, but in a coherent mixture of both. This might sound contradictory to what I said earlier, but it is not. The resolution lies in understanding what we mean by the word jump and what we mean by measurement. If we measure the energy of the atom before and after a transition, we find it has gone discontinuously from one value to another. There are only discrete energy levels, and the atom must be in one or the other when we measure it. But if we could somehow observe the atom continuously during the transition with sufficient sensitivity, we would see a more gradual evolution, a continuous change in some observable quantities, even though the final outcome will still be one of the discrete energy eigenstates. This brings me to a concept I spent much of my life developing, which I called complementarity. The idea is that quantum systems can exhibit different, seemingly contradictory properties depending on how we observe them. Light can behave as a wave or as a particle. An electron can have a definite position or a definite momentum, but not both simultaneously. The quantum jump can appear instantaneous or continuous depending on the type of observation we make. These are not contradictions but complementary aspects of a deeper reality that cannot be fully captured by any single classical description. I argued passionately with Einstein about this. He wanted a complete, deterministic theory where everything was in principle knowable and predictable. He believed that quantum mechanics was incomplete, that there must be hidden variables underlying the probabilities, that the quantum jump must have a definite trigger and trajectory that we simply had not yet discovered. I believed, and I still believe, that this search for classical determinism in the quantum realm is misguided. The quantum world is fundamentally different from the classical world we experience directly. Let me give you an analogy that might help, though all analogies have their limits. Imagine you are listening to a radio and you want to change stations. You turn the dial, and the frequency changes continuously. You can tune to any frequency you want. But now imagine a digital radio where the stations are preset. You press a button, and you jump from one station to another. There is no in between. You cannot tune to a frequency that is not on one of the preset buttons. The quantum atom is like the digital radio. The energy levels are preset by the physics of the system, and transitions between them are discrete, discontinuous. But the analogy breaks down because with the digital radio, there is still a mechanism inside the device that switches from one station to another, a physical process that takes time and has intermediate states. With the quantum jump, there is no such mechanism, no hidden machinery clicking into place. The transition is irreducibly probabilistic and, in the energy representation, discontinuous. Now you might ask, what causes an electron to jump? This is a subtle question. If the atom is left completely isolated, an electron in the ground state, the lowest energy level, will remain there indefinitely. It has nowhere lower to go. But an electron in an excited state is unstable. It will spontaneously emit a photon and drop to a lower energy state. This process is called spontaneous emission, and it is one of the mysteries that the early quantum theory, my theory of 1913, could not fully explain. The explanation came later with the development of quantum electrodynamics, the quantum theory of light, and its interaction with matter. In this theory, the electromagnetic field itself is quantized. Even in what we call empty space, the vacuum, there are quantum fluctuations of the electromagnetic field. These fluctuations can interact with an excited atom, stimulating it to emit a photon and jump to a lower state. So in a sense, the electron does not jump entirely on its own. It is nudged by the quantum fluctuations of the field around it. But the timing of any individual jump remains probabilistic, governed by quantum mechanical probabilities. There is also stimulated emission, where an incoming photon of the right energy can trigger an atom to jump from a higher to a lower state, emitting a second photon in the process. This is the principle behind the laser, a device that did not exist in my lifetime but which is a beautiful application of the quantum physics we developed. And there is absorption, where a photon is absorbed, giving its energy to an electron which then jumps to a higher energy level. I want to emphasize something important about the conservation of energy in these processes. When an electron makes a quantum jump, energy is always conserved. If the electron drops to a lower energy level, the difference in energy is carried away by the emitted photon. If it jumps to a higher level, the energy must come from an absorbed photon or from a collision with another particle. Energy does not disappear or appear from nothing. The quantum jump is strange, yes, but it still obeys the fundamental conservation laws of physics. The quantum jump also illustrates something profound about the nature of observation in quantum mechanics. Before we measure an atom's energy, if it has been perturbed in some way, it might be in a superposition of different energy states. It is not secretly in one state or another, and we just do not know which. It is genuinely in multiple states at once, in a sense that has no classical analog. But when we measure the energy, we always find a definite value, one of the allowed energy levels. The act of measurement, of interaction with our measuring apparatus, causes the superposition to collapse into one definite state. This is sometimes called the collapse of the wave function, and it remains one of the most debated aspects of quantum mechanics. I prefer to think of this not as a mysterious collapse but as the establishment of a classical correlation between the quantum system and the measuring apparatus. The quantum and classical worlds meet at the point of measurement, and it is here that the strange quantum behavior gives way to the definite, concrete results we observe. But I admit that the measurement problem, as it is called, was never fully resolved to everyone's satisfaction, and physicists continue to debate its interpretation to this day. Let me tell you about some of the experimental evidence for quantum jumps, because this is not merely abstract theory. In my time, we could observe the spectral lines, the clear evidence that atoms emitted light at discrete frequencies. But we could not observe individual quantum jumps as they happened. Technology has advanced remarkably since then. Modern experiments can isolate single atoms, trap them in electromagnetic fields, and observe them continuously. Physicists have been able to watch individual quantum jumps occur in real time, seeing an atom blink as it jumps from one state to another. These experiments have confirmed many of the predictions of quantum mechanics with exquisite precision. They have also revealed new subtleties. For instance, experiments have shown that quantum jumps can sometimes be predicted just before they occur by observing certain precursor signals. And in some cases, a quantum jump in progress can even be reversed, catching the atom in mid-transition and steering it back to its original state. This might sound like science fiction, but it is real, and it demonstrates the power of quantum control that has been developed in recent decades. These developments would have fascinated me. They vindicate the quantum theory we developed while also showing that there are layers of subtlety and control that we did not imagine. The quantum jump remains fundamentally probabilistic and discontinuous in the energy representation, but our ability to manipulate and observe quantum systems has grown far beyond what we could do in my lifetime. I should also mention that quantum jumps are not limited to atoms. The same physics applies to molecules, to nuclei, to quantum dots in semiconductors, to superconducting circuits in quantum computers. Anywhere you have a quantum system with discrete energy levels, you have quantum jumps. The principle is universal, even though the details vary from system to system. The quantum jump also connects to the broader philosophical implications of quantum mechanics, something I thought about deeply throughout my life. The existence of discrete energy levels and discontinuous transitions challenges our classical intuitions about continuity and causality. In the classical world, everything changes smoothly. If a ball rolls from one place to another, it passes through every point in between. But in the quantum world, an electron can go from here to there without ever being in between, at least not in the way we classically understand being in a place. This has implications for how we think about determinism and free will, though I must tread carefully here because these are deep waters. If the quantum world is fundamentally probabilistic, if there is genuine randomness at the base of physical reality, then the universe is not a clockwork mechanism unfolding in a predetermined way. There is openness, contingency, room for the new and unexpected. I do not claim that this solves the question of free will, but it does mean that the strict determinism that seemed to follow from classical physics is not the whole story. I also found a curious parallel between the quantum jump and the nature of thought itself. Our thoughts do not change continuously. We have insights, sudden realizations, moments when our understanding shifts from one state to another. Of course, this is just an analogy, and I would not push it too far. The brain is a classical system for all practical purposes, at least in terms of its overall function. But there is something suggestive in the discontinuity, the discrete nature of certain mental transitions, that resonates with the quantum jump. Let me return to the physics and address a question that often arises. If quantum jumps are instantaneous, does that mean information can travel faster than light? This is a good question, and the answer is no. The quantum jump itself does not transmit information faster than light. When an atom emits a photon, that photon then travels at the speed of light. The transition of the electron between energy levels is a local process, confined to the atom itself. There is no violation of relativity. However, there is a related phenomenon called quantum entanglement, which Einstein famously called spooky action at a distance. When two particles are entangled, a measurement on one can instantaneously affect the quantum state of the other, no matter how far apart they are. This does appear to involve faster-than-light correlations, but crucially, it cannot be used to send information faster than light. The correlations are statistical and only become apparent when you compare measurement results, which must be brought together through classical communication channels that respect the speed of light limit. This was another area where Einstein and I disagreed, though I must say that modern experiments have decisively confirmed the reality of entanglement. I have spent a great deal of time discussing the strangeness and the discontinuity of quantum jumps, but I want to make sure you understand that this is not merely strangeness for its own sake. The quantum jump is the key to understanding the stability and properties of matter. It explains why atoms have definite sizes, why different elements have different chemical properties, why matter interacts with light in the specific ways it does. All of chemistry, all of biology, ultimately rests on the quantum mechanics of atoms and molecules, and the quantum jump is central to that story. When you see color, you are seeing quantum jumps. The red of a rose, the blue of the sky, these arise from the specific wavelengths of light emitted or absorbed by atoms and molecules as their electrons make transitions between energy levels. The entire spectrum of visible light maps onto the energy differences between quantum states in various substances. When you use a fluorescent light or an LED, you are harnessing quantum jumps. In a fluorescent lamp, electrons and mercury atoms are excited to higher energy states by collisions. When they jump back down, they emit ultraviolet photons, which then excite phosphors that emit visible light. In an LED, electrons and holes in a semiconductor recombine, making a quantum jump that releases energy as light. The color of the LED depends on the energy gap, the size of the quantum jump. The quantum jump is also essential to understanding lasers, as I mentioned earlier. In a laser, you create a population inversion, where more atoms are in an excited state than in the ground state. Then stimulated emission causes a cascade of quantum jumps, all producing photons of the same frequency and phase, creating an intense, coherent beam of light. This technology has transformed communication, medicine, manufacturing, and countless other fields. Even the quantum computers that are being developed today rely on quantum jumps, or more precisely, on the ability to manipulate quantum states, to create superpositions and entanglements, and to read out the results. The quantum bit, or qubit, is a two-level quantum system, and computations involve carefully controlled transitions between these levels. So the quantum jump is not an abstract curiosity. It is the foundation of modern technology, of our understanding of the material world, of the very existence of stable matter. Without the quantization of energy levels and the discrete nature of transitions between them, atoms would not exist, and neither would we. As I look back on my career, on the decades I spent thinking about these problems, I am struck by how much we learned and how much remains mysterious. We developed a mathematical framework, quantum mechanics, that predicts the behavior of atoms and molecules with stunning accuracy. We learned to calculate energy levels, transition probabilities, spectral lines, chemical bonds, and so much more. The theory works. It is one of the most successful scientific theories ever devised. And yet, the interpretation, the meaning of it all, remains contested. What is the wave function really? What happens during a measurement? Is the quantum jump truly instantaneous, or does it unfold in time in ways we have not yet fully characterized? These questions engaged me throughout my life, and they continue to engage physicists and philosophers today. I developed the Copenhagen interpretation, as it came to be called, which emphasizes the role of measurement and the complementarity of different descriptions. But there are other interpretations, other ways of thinking about what the mathematics means. Some physicists prefer the many worlds interpretation, where every quantum possibility is realized in a branching multiverse. Others pursue hidden variable theories or other approaches. I respect this diversity of thought. Science thrives on debate and on the tension between different perspectives. What I am certain of is that the quantum jump, in all its strangeness, is real. It is not a mathematical artifact or a temporary approximation that will be replaced by something more classical. It is a fundamental feature of nature. Electrons do make discontinuous transitions between discrete energy levels. Energy and angular momentum are quantized. The probabilistic character of these transitions is inherent, not a result of our ignorance. This represents a profound shift in our understanding of nature, one that I was privileged to participate in. The classical physics of the 19th century, for all its triumphs, could not account for the atom. It took a new kind of thinking, a willingness to accept ideas that seemed paradoxical or counterintuitive, to make progress. The quantum jump was one of the first and most important of these new ideas. I hope that by sharing this journey with you, by explaining not just the what but the why and the how, I have given you some insight into this remarkable phenomenon. The quantum jump is where the continuous meets the discrete, where determinism gives way to probability, where our everyday intuitions fail and we must learn to think in new ways. It is a window into the quantum world, a world that is always there, underlying everything we see and touch, even though we cannot perceive it directly. The secret behind quantum jumps, if there is one, is that there is no secret in the classical sense. There is no hidden mechanism, no little gears clicking into place. The jump is what it appears to be, a discontinuous, probabilistic transition between discrete states. The deeper secret, perhaps, is that nature at its most fundamental level is not like our everyday experience. It is stranger, more subtle, more beautiful than we could have imagined. And that strangeness is not a barrier to understanding but an invitation to think more deeply, to question our assumptions, to explore the remarkable world that quantum mechanics has revealed to us. Thank you for joining me on this exploration. The quantum jump has been my companion for many decades, a puzzle, a tool, a source of wonder. I hope it has become a little clearer to you, and I hope you carry away from this conversation a sense of the profound beauty and mystery of the quantum world.